Trigonometry. So I'm gonna mostly refer to this as trig, just because it's a lot easier and quicker to say. So if you hear me say trig, it means trigonometry. All right. All right. So we're gonna just start off with some like very basic, concepts and definitions. So first thing we'll talk about is a ray. So a ray, that's the thing we will define, is a directed line segment. Okay. Okay, and what does a ray look like? It's going to have a starting point, and then it's just going to be a line that starts at this point, just coming out in some direction, and it's supposed to go forever. So this arrow indicates that it's going on forever. Okay, and we can label a ray with its starting point, so you can call it E, and then just label some other point on the ray, you can call it F. So this will be called ray EF. Okay, and E is called the endpoint of the ray. Okay.
You'd read that from right to left, or it doesn't matter, EF or FE?
Oh, okay, I wrote E twice. Yeah, so that should be read from left to right. Yeah, so that's EF right there. So that's ray EF, read from left to right. Good, thank you. And this special point E, that's called the end point of the ray. Okay. Okay, so this will lead into the definition of an angle. All right, so this is very important, extremely fundamental. So another definition, so DEF stands for definition. Okay. An angle, so I always underline the word that I am going to be defining in this. So an angle is two rays that share an endpoint. Two rays that share an endpoint. Okay, so what does this look like? So it's going to look something like this. So here I have two rays and they both share this as an endpoint. Okay, and now I can just kind of put letters onto this diagram so we can call it something. So I'll just label this point D. Again, I'll call the endpoint E, and I'll place another letter on this other ray and call it F. Okay, so we can call this, so that's why I put it in quotes, so this is how this thing would be read aloud. It would be called angle DEF. And this special point E, so it is also the endpoint, but it's also in this case going to be called a vertex. All right, so E is called the vertex. All right. Okay, so an angle is simply just this diagram. Okay, it's two rays that share an endpoint. Okay. Okay, so let's talk about creating an angle. So to create an angle, pretty simple.
Could E also be considered an angle in that or not?
Excuse me?
Could E also be considered an angle in that or not really?
So usually in our diagrams, the point that is here will be referred to as the name of the angle. So yes, usually that will be the case. We're going to get to that though, but yeah, that's true. Okay, so how do we create an angle? So to create an angle, you start with two rays. You start with two rays on top of each other. Okay, so you start with two rays that are directly on top of each other. You leave one fixed in place. And rotate the other. Okay, so let me just draw a picture of what that looks like. Okay, so so basically you're going to start with two rays on top of each other. So this ray here, look at this as two rays on top of each other. And then I'm going to take one of those two rays and just kind of rotate it out here. And now I have both of these rays. And this is how you create an angle. Okay. So we also have some terminology attached to this diagram. So that's called the initial side. Okay, so this is the ray that remains fixed. That's the initial side. And this guy is called the terminal side. Okay, initial side, terminal side, and this is also, and this endpoint here again is the vertex. Okay, so the initial side stays put, and then the terminal side is the side that you rotate, or it's the ray that you rotate out to create your angle. All right, so it's kind of like an intuitive way as to how angles are created. Okay, so here's a very important piece of notation. So notation. So we will often use the Greek letter. Okay, so we will often use the Greek letter. So it's drawn like this, the symbol, and it's called theta, theta, T-H-E-T-A, okay, to denote an angle. Okay, so maybe that Greek letter seems kind of familiar to you guys. If not, no problem. So it's drawn like this. It's like a circle with a horizontal line through the middle, and it's pronounced theta. Okay, so how does this look in practice? How does it look in like a diagram setting? So here we have an angle, and you will just place the theta symbol right there, kind of like at the vertex. And this would be called angle theta. Okay, so that's just conventionally what is used to denote an angle. It's usually the Greek letter theta. It doesn't have to be because it's just a variable, but that's just conventionally what is used. And that's what you'll see in a lot of textbooks and a lot of math writing. Okay. Okay, so now that that is all set up, we can start talking about measuring angles. So another definition. So the measure of an angle so the measure of an angle is the amount of rotation from the initial side. It's the amount of rotation from the initial side to the terminal side. Okay, so let me just kind of scroll up to where we created that angle with the initial side and the terminal side. So the measure of this angle that was created here, it's going to be the amount of rotation that the terminal side went away from the initial side. Okay, so that's how that's what it means to find the measure of an angle. It's the amount of rotation from the initial side to the terminal side. So how much did we rotate from here to there? All right, so this should seem fairly intuitive. I know I'm just kind of stating very intuitive facts, but I kind of need to put like a mathematical foundation to these intuitive facts. All right. Okay, so that's what the measure of an angle. Okay, so now let's talk about degrees. So what units do we use to measure angles? There's going to be two units, degrees and radians. Okay, so we'll first talk about degrees, which is probably the more familiar unit. Okay, so 1 degree, by definition, is 1 over, so it's 1/360th of a rotation. 1/360th of a rotation. Okay, so thus, 360 degrees is a complete rotation. Okay, so again, this should seem sort of familiar. So 360 degrees will be a full rotation, all right? And 1 degree is just 1/360th of that, all right? Okay, and the notation for degrees, do I have it here? No, okay, so you will notate this as 1 degree, notationally will be 1 with a superscript, and then in the superscript will just be like a little open circle. Okay, so that should look familiar from like when you're reading the temperature outside or something. Okay, so 1 degree, you will often shorthand write it as 1 superscript circle. Okay, all right. Okay, so just give me 1 second, guys, hold on. Sorry about that. Okay, so so far none of our work has been in the XY plane, so let's kind of move into that setting. Okay, so we will very often draw angles in the XY plane. Okay. Okay, so far all of the angles I have drawn, they have just been kind of just out in space. They've just been like nowhere pretty much. But usually we will look at our angles in the XY coordinate plane. Okay, so you guys know what that looks like. That's just like the set of axes. This is the x-axis, and that's the y-axis. All right, so that should look familiar. Okay, so another definition. So we're going to talk about what it means for an angle to be in standard position. Okay, so this very important. So an angle is in standard position. So that's the word that I'm defining. An angle is in standard position if its vertex is located at the origin. Okay. If its vertex is located at the origin. Oh, okay, so, and there's just a little more to this definition, sorry. So if its vertex is located at the origin with its initial side, extending along the positive x-axis. right. Okay, so I'm going to show you guys some pictures of what this looks like, but just recall the positive x-axis. It's just the part of the x-axis that has the positive numbers. So it's going to be that part. It's going to be the right side of the x-axis, the right side of the origin on the x-axis. All right, so now I have a picture of an angle in standard position. So let's just go to that. Right. So you can kind of see like the definition in this picture. So you can see that the vertex of the angle, it's precisely at the origin, right? And the initial side is lying exactly on the positive x-axis. And that's it. And of course, we have two rays that share an endpoint. So this is an angle, and it's in standard position because the vertex is at the origin and its initial side is lying on the positive x-axis. All right, so this is what it looks like.
So even if it makes a full rotation, as long as the initial side's on the x-axis, it's still considered to be in standard position?
Yes, absolutely.
Okay.
Yeah, and also the vertex, this part, has to be at the origin. But yes, definitely. All right. Good, good. So that's a nice picture. We're going to be dealing with pictures like this very often for the next 2 weeks or so. So yeah, so it's good to get familiar with this. Okay, good. So now we're going to just talk about quickly what it means for an angle to be positive or for an angle to be negative. All right, so another definition. Okay, I know that there's a lot of like definitions here. It's because we need to set up like the groundwork for our computations. Okay. Okay, so positive, negative. So an angle is positive. Is positive if, okay, so that's the word I'm defining. An angle is positive if it's measured in the counterclockwise direction. Counterclockwise direction. Okay, and what that means is you're taking this terminal side and you're moving it in the counterclockwise direction, which is this way. That's counterclockwise that way. Okay, so if you do move that terminal side counterclockwise, that angle is going to be positive. So the measure of the angle will be positive. So this angle here in this picture, this is a positive angle because the terminal side was rotated counterclockwise. Okay, so this is actually, that's a positive angle. Good, so what does it mean for an angle to be negative? Well, it's just going to be measured in the clockwise direction. Okay, so let me just write that quickly, just for the sake of completeness. So an angle is negative. An angle is negative if it's measured in the clockwise direction. Okay, so we're going to see examples. So that just means that that terminal side was rotated in a clockwise direction. Okay, we're going to see examples of both. So let's see that right now, actually. So example, the first thing will be, so here's kind of here's the question or the task. Draw a 90-degree angle in standard position. Draw a 90-degree angle in standard position. Okay, so 90 degrees. So the number you look at is 90. That's positive, okay? Obviously, 90 is a positive number. So that means we need to rotate counterclockwise, okay? So what is this going to look like? So it's in standard position. So we're going to put our vertex right here at the origin. We're going to have our initial side right here. And we're just going to rotate the terminal side 90 degrees. Okay, so it's just going to look like this. So it's kind of hard to see because it actually is exactly on the y-axis. But yeah, that's what it's going to look like. Okay, 90 degrees. Okay, and just note that we are moving counterclockwise because 90 is a positive number. We're going to move in the counterclockwise direction. All right, so any questions on this? Okay, and a 90-degree angle is also referred to as a right angle. So let me just write that quickly because we're going to use that later. Note, a 90-degree angle is also called a right angle. Okay, very good. Let's do another one. So how about negative 45 degrees? So draw negative 45 degrees in standard position. Okay, so whenever you see the word standard position, you know that you have to draw an XY plane. Okay, you have to draw your XY axes. Okay, because that's built into the definition of standard. It's built into the definition of standard position. All right, so here is my XY plane. So I want to do negative 45. So now negative 45 is, of course, a negative number. So we need to move in the clockwise direction 45 degrees. All right, so here is my initial side. And now I want to move clockwise 45 degrees. All right, so that's just going to look like this. Okay, and we spun out that way. All right, we spun out in the clockwise direction, and this will be negative 45 degrees. All right. So any questions about this? All right, so I just have some more examples of angles in standard position. I figured it would be better to just grab an actual picture of it as opposed to me drawing. So let's just get that. Right, so here, let me just kind of talk through this picture quickly. So here we have the angles 0 degrees, 90 degrees, which I did above. I guess I didn't need to do it. 180 degrees and 270 degrees, all drawn in standard position. Okay. So we're gonna see later that these angles turn out to be very important. They're gonna be very important for us. So, all right. So I hope everyone sees that these are in fact in standard position. And these are all positive angles. All right, we went counterclockwise to draw these guys. All right. So let me just describe very quickly what this is. All right. So here are the angles 0, 90, 180, 70 degrees. Okay, so here are the angles 0, 90, 180, and 270 degrees in standard position. Right, so we're just kind of trying to reinforce this concept. Excuse me. Okay, good. So we have degrees. So far, our unit of measurement for these angles have been degrees. Sometimes that is not so preferable because it's out of 360, and that number 360 is kind of just like an arbitrary choice. Like, why did we choose 1 degree to be 1/360th of a rotation? There really is no reason for that. That's just kind of conventionally how people did it whenever it was made up. So it seems kind of arbitrary. So a better unit of measurement for angles are radians. All right, so now let's discuss what this means. Okay, radians. Let me just move this down so it's not a part of the discussion. There. Okay, radians. Okay, so all right, so we can also measure angles. We can also measure angles using radians. And of course, I'm going to define and explain what that is using radians. Okay, so here is the setup. Here is the definition of a radian. It may seem a little confusing, but we will work through it. So here we go. So here's the definition of a radian. Okay, so here's the setup. So let C be a circle of radius r. Of radius r, okay? A radian is the measure of a central angle that intercepts an arc. Okay, so measure of a central angle that intercepts an arc of length r. Okay, so when I first read this definition, it was actually kind of confusing. I don't really know what this means. Like when I first read it, I didn't really know what this meant. It's a little confusing. So I'm going to show you guys a picture. And when I saw this picture, it kind of cleared everything up. But first, let me just note here the connection with this radius r. So the circle has radius r, and the arc that the central angle intercepts has length r. Okay, so that's important. So now let's look at the picture. So this, I hope, will clear things up. Right. Okay. Good. So here we go. So we have a circle here. I called it C. It doesn't really matter. This is circle C. It has a radius. So we call this R in the definition. And now I make a central angle. So that's this guy. That's this angle that intercepts an arc of radius R. Okay, so move this green line segment until it intercepts an arc on the circle of length r. Okay, that's what this kind of dark red is. And the angle that it makes by definition is 1 radian. Okay, so again, you move this green line segment until it intercepts an arc of length r. Okay, that's your first step. So you did that. So this has length r. After you have done that, the angle that it makes by definition is 1 radian. Okay.
And the arc is that red piece.
Yes, the arc is this kind of darker red piece right here.
Does that also include like that whole angle within it, or?
No, so like this is like some sort of, this is like a, you know, this is something that has length. You know, if you theoretically you could measure the length of this dark red piece, and when that dark red piece has a length of r, where r is the same length of your radius, the angle it makes is 1 radian.
Okay.
So the angle right here, by definition, is 1 radian. Okay. So I encourage you guys to maybe like kind of stare at this for a little longer, like after class, if it doesn't make sense. And of course, you can ask me some questions about it. All right. I'm just going to erase this because I think it just clutters up the thing.
So once the angle intersects with that arc, the arc length will be equal to the radius? Or
No. So first, you need to move this light green segment far enough so that this arc becomes length r. Because you see, if I just move this green segment here, you would just get this piece. And this piece is not length r yet. So you're not done. So you move this green segment until you intercept an arc of length r. Okay.
that also depends on, how do I say it though? Like how big the angle is. I mean, that might not be like the right way to.
So the angle comes last. So really, like the data you need is the radius.
Okay.
Yeah. Is there anything else that's confusing?
No, that's pretty. Oh, sorry. I thought you were asking me.
No, he probably was. I just have a question. I'm super confused about the R representation. The R representation just for radius, not for radian.
R?
Yes.
Oh, that was just like a letter that I assigned to be the radius.
Oh, okay. Because okay, yeah. I thank you.
Yeah. So just very quickly, if the radius of a circle was 3, then just r would be a variable that equals 3. That's what I meant. Let r be. It's just the radius. So it's a variable. All right. So this is not super important. Like you don't need to know precisely what a radian is, but I remember I went through like all of high school not really knowing the definition of a radian. All right. So I think it's just important to know what it is. All right. So let's just keep going. Okay, good. So we need to just talk about the circumference of a circle. So recall that the circumference of a circle is given by the formula. So the circumference of a circle is given by C for circumference is equal to 2 pi times r, where r is the radius. So 2 pi number of arcs of length r will fit around the circle. Okay, so if the distance around the circle, which by definition is the circumference, it's the perimeter of the circle, is 2 pi r, that means that a 2 pi number of r's, arcs of length r, will fit around this circle. Okay, so I can take 2 pi number of length of arcs of length r that will fit exactly around my circle. Okay, and the whole point of this is that 2 pi radians will equal 1 full rotation. Okay, and in degrees, that will be 360 degrees. Okay. All right, so now we are going to talk about converting between the two units. All right, so it will be very useful to know how to convert from radians to degrees and vice versa from degrees to radians. So let's just talk about this quickly. Okay, first let's talk about radians to degrees. So first one, you're given radians and you want to go to degrees. So what you do is you just multiply your radians by, so the formula is multiply your given radians by 180 degrees over pi. Okay, so if you're given some quantity in radians, to turn it into degrees, you just multiply that by 180 over pi. All right, so example, convert pi radians to degrees. Okay, so as the formula states right here, I just need to multiply my radians by 180 over pi. So you do your radians, which is pi, and you multiply by 180 over pi. Okay, and what will this come out to? Well, this is actually a very easy one. The pi's in the top and bottom will cancel, so you're just left with 180 degrees. So that's the answer. So pi radians is 180 degrees. Okay. So any questions? So just please let me know if this is not clear. This is very important topic. Okay. So let's do another. So let's convert pi over 4 radians. So convert pi over 4 radians to degrees. Okay, well, the process is exactly the same. You take your radians and you multiply, so I'll put a little dot for multiplication. You multiply by 180 degrees over pi. Okay, so again, the pi's will cancel out. That's always going to happen. Well, usually it will happen. So you're just left with 180 over 4. Good, and then you just work this out very quickly. You can use a calculator if you want. 180 divided by 4 is 45. Okay, so the final answer here will be 45 degrees. All right, so that will be that. So we just did radians to degrees. Okay, given radians, tell me what that is in degrees. So any questions? Okay, so let's go the other way around. So let's go from degrees to radians. Okay. Degrees to. Okay, degrees to radians. And what is the formula? The formula is simply multiply by pi over 180. Okay, so you just take your degrees, multiply it by pi over 180. So, example. Convert 60 degrees into radians. Okay, so as the formula says right here, you take your degrees, So you take 60 degrees and then you multiply by pi over 180. Okay? So you multiply by pi over 180, you will get that this is equal to 6 pi over 18. So remember, we're multiplying fractions, so you just multiply straight across, and then you can just reduce this fraction, pull out a common factor of 6 from the top and bottom, and this will be pi over 3 radians. Okay, so that would be the answer here, pi over 3 radians. Good, good, good. All right, so let's do the last, I have the last example for this. Let's convert 270 degrees. Convert 270 degrees into radians. Okay, what does the formula tell us? Well, we ought to just multiply 270 by pi over 180. That's what it is. So it'll be 270 times pi over 180. Okay, so with these, you're going to want to simplify this as much as possible. So you can pull out a factor of 9 from 270 and 180. So this is 9 times 30 pi divided by 9 times 20 pi. Then the 9s will cancel. You get 30 pi over 20 pi. Pull out a 10 from the top and bottom, you'll get 3. Oh, sorry, there should not be a pi down here, excuse me. Yes, sorry, I wrote a pi in the bottom by accident in the denominator. Okay, excuse me. Okay, so you get 30 pi over 20. You can now pull out a 10 from both 30 and 20. You just get 3 pi over 2. Okay. So that will be the answer. So 270 degrees is 3 pi over 2 radians. Okay, good. So now I'm just going to list out some very common degree to radian conversions that you should just kind of know off the top of your head. So just some very common ones. All right, so here are just some ones that are important to know. Okay, so these are extremely common. So the first one will be 30 degrees is pi over 6 radians. The next one, 45 degrees is pi over 4 radians. So I definitely would suggest noting these down somewhere because these are used. So these angles in particular are going to be used very often in our class. The next one will be 60 degrees is pi over 3 radians. Okay. 90 degrees. This is pi over 2 radians. Okay, next, 180 degrees, which I think we did already. This is pi radians. 270 degrees, which we also did, is 3 pi over 2 radians. And the last one, 360 degrees, this will be 2 pi radians. All right, so as I said, these are just like very important angles that it will be useful to just switch between from degrees to radians in a fast manner. All right, so it will just be good to have these kind of in the back of your head. And of course, you can prove all of these. You can show that all of these things I've written here are true just by using our conversion formulas up above. All right, so you can definitely check what I wrote here just by doing them yourself using the formulas. Okay. Okay, good. So now we're going to start to talk about triangles, which is kind of like the core of trigonometry. All right, so trigonometry is like the study of triangles and their angles and whatnot. So now we're gonna get into that. All right, so any questions on anything before I start? Okay, all right, so let's start off with a right triangle. So definition, a right triangle is a triangle is a triangle that contains a 90-degree angle. Okay. And the side that is opposite the 90-degree angle also has a special name. It's called the hypotenuse. So let's just write that quickly. The side opposite the right angle is called the hypotenuse. Okay, so what does it look like? So here's a picture of a right triangle. Okay, and here I've drawn the right triangle to be, the right angle to be on this left side here. Okay, so here's a right triangle. And usually we will denote the hypotenuse with the letter C. So C here is the hypotenuse. All right, so C is the side that is opposite from the right angle. Okay. All right, good. So with the right triangle comes a very important theorem or a formula, and it's called the Pythagorean theorem. Okay, so very classic. There's so many proofs to this. It's like one of the most proved theorems out there. So this is called the Pythagorean theorem. So I believe even a former US president supplied a unique proof to the Pythagorean theorem, which is, I think, so cool. I forget which president it was, but you can look that up really easily. So I think that's a fun fact. Okay, so what does the Pythagorean theorem tell us? Okay, so let a right triangle have legs of length A and B and a hypotenuse of length C. Okay, so the legs and hypotenuse satisfy this very special equation. Then we will have that C squared is equal to A squared plus B squared. Okay, so we have this very nice formula that holds. James Garfield. Okay, so Luke just wrote in the chat that it was actually former President James Garfield who supplied a proof for the Pythagorean theorem. Awesome. Thanks, Luke. That's very cool. Okay. So that is the Pythagorean theorem. Let's just use it quickly. Let's just do a few practice problems with this guy, just so we're totally comfortable using it. Okay, so I'm going to give you a right triangle. Okay, so it's going to have legs 3 and 4, and I want you to find, so the question will be to find find C. Okay. Okay, so we're just going to use the Pythagorean theorem. So by the Pythagorean theorem, we know that C squared, which is what we're looking for, will be equal to the lengths of the legs. So you do 3 squared plus 4 squared. Okay, so you square the lengths of the legs and then you add them together. So 3 squared plus 4 squared. So C squared will be equal to 9 plus 16, because 3 squared is 9, 4 squared is 16. C squared is equal to 25. Good, and now you can take the square root of both sides, and C will be equal to 5. So that would be that. So you may be asking, oh, well, we took the square root of both sides. Why did I not introduce a plus or minus? That's a great question. And the reason being is because we're talking about the length of a shape, and it really wouldn't make sense for the length of the hypotenuse to be -5. Okay, length is supposed to be a positive quantity. So that's why we kind of reject that negative square root. All right, so C will be 5. Okay, good, one more. So I have a right triangle again. I'll have that the hypotenuse is 3, this leg is 5, but this leg is B, and the question will be to find B. Okay, good. So would anyone like to maybe set up the equation here to solve? Would someone like to apply the theorem for me and tell me how to solve this guy?
It'd be 5 squared plus B squared equals 13 squared.
Yes, exactly. Thank you. And so can you just explain why you put 13 squared alone on the right side of the equation?
Well, so you have two sides that are going to be squared. Well, I know that whatever you do to one side, you must do it to the other side too. I mean,
right. So I'm just asking, why did you set it equal to 13 squared? Like, why did you not do like 5 squared plus 13 squared is equal to B squared? What's special about this 13 that you put it alone on the right side of the equation?
Can I try to answer?
Yeah.
Because it's the only side that's not connected to the right angle.
Right. So it's the hypotenuse.
Yes, but I was trying to sound better. I don't know.
Yeah, no, that's totally true. Right. So it's not connected to the right angle. It's across from it. So it's the hypotenuse. Did someone say something? Sorry, I thought I heard something. Yeah, so if you so in the statement of the Pythagorean theorem, you set the hypotenuse squared equal to the 5 squared plus B squared. That's what goes alone on the one side of the equation, all right? So it will just be 13 squared, the hypotenuse squared, is equal to 5 squared plus B squared. All right, and this 13 is here because it's the hypotenuse. That's the statement of the Pythagorean theorem. Good, so you just work this out very quickly. You'll get that 169 is equal to 25 plus B squared. Good, so now you just do some algebra. You get that B squared is 144. Take the positive square root of both sides. You'll get that B is 12. Okay. So that's the Pythagorean theorem very quickly. All right, so I hope that's pretty simple. Okay, good. So some more definitions. Okay, so we're going to need to talk about what it means for sides of a triangle to be opposite and adjacent with respect to a given angle. So I'm just going to kind of draw a picture first. Okay, actually, I'm going to draw it slightly differently, excuse me. So we have this right triangle here. I'm going to draw it a little differently than usual. Oh, I don't want to do that. Okay, so here's the right angle, and I'm going to label this angle here on the left side, I'm going to call that theta. Okay, now with respect to theta, we're going to have something called the opposite side and the adjacent side. Okay, and it is what it sounds like. So the opposite side will be the side that's opposite from theta. So that's going to be this side right here. So that will be opposite. Very good. And the adjacent side will be the side that's literally adjacent to theta. It's going to be right here. All right, it's going to be this side. Okay, and then the hypotenuse is still called the hypotenuse. That's just the side that's opposite from the right angle. Okay, so that's the hypotenuse. Okay, so we're going to need this. So I'm just going to write this now. So the side closest to theta is called the adjacent side.
So given that this triangle would be also considered an angle, you could also consider that vertex point to be the angle too, like when I mentioned earlier.
Okay, so this vertex, that's not the angle. The vertex is like a part. Oh, I see what you're saying. Like if I just like if I labeled this like A or something.
Yes.
Oh, okay, I see what you're saying. Yes, so you will see it like kind of both ways. If you kind of label the vertex A, you could refer to this as angle A, sure. But I think what we will mostly be doing is having it labeled how I have it. You put it inside the triangle with like a little arc, like that.
Oh.
But yes, the way you said it, it will be seen like that sometimes. But here, this will just be angle theta. Okay, so as I said, the side closest to theta is the adjacent side. So that's right here. Okay, and the side across is called the opposite side. Okay, so I hope that's clear. Have an angle theta. So you always have to start by like saying which angle you're doing this with respect to. So I'm starting here at this angle theta, then that will determine an opposite and an adjacent side. But just note, if we were actually working up here, what if our angle was up here? This was our theta. Then that would be the opposite, and this would be adjacent. Okay, so just note the terms adjacent and opposite, you always need to know which angle you're at first. Then you determine what is adjacent and opposite to that angle. Okay, because if I place my theta up here, then the adjacent and opposite sides would be different. Okay, so it's always with respect to some angle. So that's very important. But here we did it with respect to this angle here. So that would be opposite and that would be adjacent. Okay, good. So a quick example of this. All right, so we have a triangle. This will be theta. It's a right triangle. Okay, so I'll have A, B, and C. Now, I would just like you guys to tell me with respect to theta, I want you to tell me B is the what side, A is the what side, and C is what. So I'm looking for the words opposite, adjacent, and hypotenuse. Let's think about this for a second, and then if maybe someone wants to tell me what to fill in, I would I would appreciate that. So here is kind of like my starting point. I'm here at theta. Now this will determine an adjacent and an opposite side. So let's think about that for a moment.
Can I say all of them or just one?
All of it, yeah. Go for it.
All right, you can probably hear my dog in the background right now.
Oh yeah, I do. That's cool. That's cool.
B is adjacent, A is opposite, and C is hypotenuse.
Yes, exactly. B is adjacent, excellent, because it's literally right next to theta. A is opposite, and C is hypotenuse. Awesome. Thank you, Jen. So B is adjacent. A will be opposite. And C, that will not change with respect to theta. The hypotenuse does not depend on theta. That will always be the hypotenuse. Very good. So just again, let me just note that if theta were up here, the answers would be different. B would be the opposite and A would be adjacent if theta were up here. Okay, so these questions always, you need to fix your angle first. It's respect to an angle. And then you determine your opposite and adjacent. All right, so that's very important. Very good. Okay, now we're going to get to the sine and cosine functions. Okay, so trigonometric functions. Trigonometric. Okay. Okay, so here we go. So definition. Given a right triangle with non-right angle theta, so we have the following definitions. So theta is just one of the angles that's not the right angle in the right triangle. Okay, so we have the following definitions. Sine of theta. This will be opposite divided by hypotenuse. And what do I mean when I say opposite divided by hypotenuse? It's going to be the length of the opposite side divided by the length of the hypotenuse. So that by definition is sine of the angle theta. Okay, good. Let's do the next one. The next one will be cosine theta. So this here is sine, S-I-N-E. The next one will be cosine theta. This will be adjacent, the adjacent side divided by the hypotenuse. Okay, and this is cosine. Good, so we have one more, which is actually has to do with these two, and that's going to be called tangent of theta. So this, by definition, is going to be sine theta over cosine theta. That's literally the definition of tangent. It's just the ratio of sine and cosine. So we can actually work this out explicitly. So sine of theta, remember, by definition, is opposite over hypotenuse. So that's sine of theta. And then cosine of theta is adjacent over hypotenuse, right? So now if I actually just divide these fractions, so do the keep, change, flip, you will get that this, this complex fraction here will reduce to just opposite over adjacent. Okay, and this is tangent. Okay, so thus tangent is just the length of the opposite side divided by the length of the adjacent side. Okay, and a very common trick for remembering these guys. So maybe this will sound familiar from high school. So here's a trick. You can think of the word SOHCAHTOA. So hopefully that doesn't bring back any bad memories from high school. So SOHCAHTOA. And how this is read as, you can think of it as like S for sine is O over H, opposite over hypotenuse, then CAH. This is like the C is for cosine, which is adjacent over hypotenuse. And then the TOA, the last part, is tangent, which is opposite over adjacent. All right, so that's kind of the way I remember it still. So I'll just kind of think of this in my head. So sine, this big S, refers to opposite over hypotenuse, and so on. All right, and then you can kind of read this aloud as SOHCAHTOA. Right. Good. So now let's do an example where we actually compute some trigonometric functions. So find sine theta and cosine theta. Okay, so I'm going to give you guys a right triangle. So now I need to tell you what angle is going to be theta, and it's going to be this one on the left side. So here's theta, and I have the side lengths 8, 15, and 17. Good. So in order to find sine and cosine, what are the pieces of information that you need? You need the opposite side, you need the adjacent and the adjacent side, and you need the hypotenuse. Okay, so let me list all of those pieces of information right here. So here, the adjacent side, which I will shorten to ADJ, just is easier. So you go to theta, and you go to the side that's adjacent to it. That's going to be 15, okay? So remember, adjacent and opposite, they're always with respect to some angle that I fixed already, and here the angle has been fixed. All right, so adjacent is 15. Good, how about opposite, which again, I'm going to shorten to OPP. Makes it a little easier. Opposite will be the thing across from theta, which is 8. And the hypotenuse, I'll shorten to HYP. That will be 17. Good. Now it's very easy to find cosine and sine. So cosine of theta, by definition, is adjacent over hypotenuse. Good. So now let me just plug in everything. Adjacent is 15. So I put that in the numerator. And then in the denominator goes the hypotenuse, which is 17. So it'll be 15 over 17. That's the first one. And now let's figure out sine. Okay, so firstly, by definition, sine of theta is opposite over hypotenuse. And good, we have all of this information up here. Opposite is 8, so that will go in the numerator. And then you divide by the hypotenuse, which again is 17. So that will be that. Good, so any questions on this? Okay, let's do another example. Okay, example, find sine theta and tangent of theta. Okay, with this right triangle. Okay, so where am I going to put theta here? I'm putting it actually in the top. So it's a little different. So theta is here now, it's in the top. Okay, good. So I'm going to have a leg of 7 and a hypotenuse of 25. Okay, so this was all the information that was given. Okay, so now we want to find sine of theta. Sine of theta will be opposite over hypotenuse. Okay, so we need to find the opposite. It was not given to us, okay? The opposite side was not given to us. So does anyone have any ideas? How can we find this missing opposite side that we need? Do we know any theorems?
The Pythagorean, yeah, I don't know how to pronounce it.
Yeah, exactly. Pythagorean theorem, yes. Thank you. Good, good. So let me just write this very quickly. The opposite side length is not given to us. Okay, which we need. We need the opposite side length to find sine of theta, because sine of theta is opposite divided by hypotenuse. So we need this opposite side length. And as Faye said, yes, we can definitely use the Pythagorean theorem. So let me just write this out quickly. Use Pythagorean. Very good. So the equation that you set up, it's the hypotenuse is equal to 7 squared plus the missing side squared. So we will set up the equation. 25 squared is equal to 7 squared plus b squared. So you work this out, you'll get that this is 625 is equal to 49 plus b squared. And you will get that b is actually equal to 24. Okay, so thus, opposite here is equal to 24. Okay, so we just figured out this opposite side now. All right, so here's our new triangle. I'm going to draw it again. So no, it's not a new triangle, it's the same triangle, but now we have more information. Theta was up here, and we just figured out that this is 24, this is still 25, and this is 7. Good, so opposite is 24. What else do we need? We also need adjacent. Adjacent is 7, and hypotenuse will be 25. Okay, so now we have all the pieces of information we need to find sine and tangent. Good, so let's do that. So sine of theta, by definition, is opposite over hypotenuse. Good, so we just figured out that the opposite side is 24. So that's why we did this whole Pythagorean theorem thing, is because we needed to find this opposite. And the hypotenuse was already given to us, that's 25. So that's this one. And now let's do tangent. Tangent of theta, by definition, is opposite over adjacent. Okay, opposite is 24. And then you divide it by the adjacent side, which is 7. Good. And that will be that. Okay, so this question kind of forced us to do an extra step. We needed to find one of the missing leg lengths. And then we can fill in our opposite, adjacent, and hypotenuse. Okay, good. Now I need to very quickly talk about the reciprocals of sine, cosine, and tangent, because they have special names as well. So very quickly, the reciprocal functions. Okay, so the reciprocals of sine, cosine, and tangent have their own names. Okay. So just recall that the reciprocal of a number b is the number 1 over b. So we're going to just look at 1 over sine, 1 over cosine, and 1 over tangent. Those are, by definition, the reciprocals. Okay, but each of those things I just said have their own names. The first one is called secant. Secant. And this is where and the notation for this, it's SEC theta, secant of theta. And this will be the reciprocal of cosine. It's reciprocal of cosine. So in terms of the adjacent and hypotenuse definition, recall that cosine was adjacent over hypotenuse. So secant will be the flip of that. It will be hypotenuse over adjacent. Okay, so we took the fraction for cosine, which is adjacent over hypotenuse, and we flipped it. We took its reciprocal to obtain hypotenuse over adjacent. So that is secant of theta. Good, so we're gonna have two more, one for sine and another for tangent. So next will be cosecant. Cosecant, and the notation for this is CSC, CSC theta, cosecant theta. And this by definition will be the reciprocal of the sine function. It's the reciprocal of, it's 1 over sine. Good, so in terms of our opposite and hypotenuse, so recall, sine of theta is opposite over hypotenuse. So cosecant, the reciprocal, will be the flip of that fraction. So it'll be hypotenuse over opposite. Okay, that's how that is obtained. Last one, cotangent. Okay, and the notation for this is COT, cotangent theta, and this will be this will be the reciprocal of the tangent function, 1 over tangent. Okay, and then you work this out. So tangent is opposite over adjacent. The reciprocal of that will be adjacent over opposite. Okay, so just keep these in mind. You're gonna have some of these on the homework, but I'm not gonna do it now. But I think it's pretty self-explanatory. All right, so we just gave the reciprocals like their own notation and names. All right, so any questions? We're gonna go now into the last part of class. Okay, so the last thing we will do, we'll do trig values of special angles, okay? This is kind of nice. Trig values of special angles. Okay, so I'm just going to type very quickly. So we can actually obtain closed forms for the trig values, for the trig functions evaluated 30, 45, and 60 degrees. Or in radians at parallel right. So we can actually obtain closed forms for the trig functions, sine and cosine, and the rest of them, evaluated at 30, 45, and 60 degrees, or in radians at pi over 6, pi over 4, and pi over 3 radians.
When you say closed forms, what do you exactly mean?
Okay, by closed form, I mean it's just going to be like, it's not going to be like a never-ending decimal. It's just going to be just like a nice number.
So rational, like.
So some of them will be irrational, but we're going to be able to just write it in a nice closed form. Like maybe it'll be like the square root of 3 divided by 2. That's a closed form, as opposed to writing it out in like a nasty, never-ending decimal expansion. That's what I mean by closed form. It's just going to be like a nice expression.
Okay.
Yeah. So we're gonna now work at finding sine and cosine at 30, 45, and 60. And these actually have some nice closed forms, which we'll talk about. Okay, so first thing, I'm gonna move through this sort of quickly. It's gonna be called the 30, 60, 90 triangle. Okay, so this is a geometry classic. Okay, so what is a 30, 60, 90 triangle? Well, first of all, let me just draw the picture. A 30, 60, 90 triangle, it's a triangle whose angles are precisely 30 degrees, 60 degrees, and 90 degrees. So it's a right triangle. This will be 30 degrees up here, and this one will be 60 degrees, okay? Good. Okay, so a triangle with such angles, so when I say such angles, I mean with angles 30, 60, 90, with, I'll put an S there, with side length S across from the 30-degree angle, so I am labeling the side across from the 30-degree angle as S, okay? And you'll see why in a second. So the length of the side opposite from the 30-degree angle is S. So we actually can get expressions for the hypotenuse length and this other leg length. Has hypotenuse length 2S, so it's actually double this side, and other leg length S times the square root of 3. Okay, so this is a very nice fact from geometry. Okay, this is a very classic fact. So if you have a 30, 60, 90 triangle, you label this side S, you know for a fact that this hypotenuse will be twice the length of S. Okay, that's going to be 2S. And then this other leg length will be S multiplied by the square root of 3. Okay, so this is a theorem of geometry, and it's a very standard fact. I'm not going to prove this fact, but it is easily provable. Okay, but we're just going to take it for granted.
Is that just only with the 30, 60, 90 triangles?
Yes, very special case, yes. Then you have this relationship. If this is S, then you know that this hypotenuse will be twice S, 2S, and this will be S times root 3. So if S was 1, for instance, this would be length 2, and this would be length root 3. Okay, so we're in very good shape. We can find now sine and cosine of all these angles very easily. So I'm going to copy this triangle down here, so we're going to use it. Okay, very good. So I'm just copying it down because we're going to use it. Okay, so thus, here we go. We can find the sine of all of 30 degrees now. So sine of 30 degrees. Okay, so remember for sine, we need to go to the 30 degrees, and then we look at opposite over hypotenuse. So this will be opposite. So I'm just going to write this, opposite over hypotenuse. So opposite from 30 is S. So I will put that in the numerator. And in the denominator goes the hypotenuse, which is 2S. And look what happens. You actually get a very pleasant cancellation. You get that this is equal to 1/2. The S's cancel out. How nice is that? So sine of 30 degrees is 1/2. So that's a nice closed form. Okay, good. Now let's do sine of 60 degrees. Okay, so now we're changing our angle that we're doing this with respect to. So now we need to do opposite over hypotenuse with respect to this 60-degree angle. Okay, so now we're moving over here. So if we're standing at the 60-degree angle, the opposite will be s root 3, and the hypotenuse will be 2s. Okay, again, you have the s's canceling out in the top and bottom, and this will just be square root of 3 over 2. So, Saeed, that's what I meant by a nice closed form. It's just represented as just like a fraction like this. Good, so that's very nice. So now let's do the same thing for cosine, okay? All right, so cosine of 30 degrees. So cosine, recall, it's adjacent over hypotenuse. Good, so I go to 30 degrees. I go to the adjacent side, which will be s root 3. So I put that in the numerator. Next, I divide by the hypotenuse, which is 2s. Good. The s's again will cancel out. You're just left with the square root of 3 over 2. Very nice. Last one. Let's do cosine of 60 degrees. So now I'm changing my reference point to 60 degrees. I need to look at the adjacent over hypotenuse from this point of view. Adjacent is s, hypotenuse is 2s. So I will do s over 2s, which is 1/2. So very, very nice, very fundamental. We're going to be using these values all over the place, okay? Good. Okay, one last thing. I need to talk about 45 degrees, okay? So we can also get a nice form for 45 degrees. So let's do that. So in this case, it's going to be the 45, 45, 90 triangle. Okay. So a triangle. All right, a triangle with such angles. And what I mean by that is it has angles 45, 45 degrees, and of 90 degrees. A triangle with such angles and leg lengths S. This has hypotenuse length s times the square root of 2. Okay, so this is again a very classic and standard fact from geometry. Okay, and what's the picture? Here's the picture. So I have a right triangle, okay, but now I have 45-degree angles here. That's 45, and this is 45. And if I know that these leg lengths are s, and they have to be the same because they're opposite from equal angles, so these will be SS, you know that the hypotenuse length will be s times the square root of 2. Okay, so this can be proven with the Pythagorean theorem, I believe. This one can be proven with the Pythagorean theorem. The 30, 60, 90 triangle, you need to do something else, but this can be proven with the Pythagorean theorem. Yeah, because you just do s squared plus s squared is equal to c squared. You get 2s squared is equal to c squared. Divide by 2. Yes, right? Yeah. All right, anyways, I don't want to go there right now. Good. So we're just going to, now from this, we can find sine and cosine of 40 degrees. Okay. Good. So thus, we have a nice closed form for 45 for sine of 45. So remember, sine is opposite over hypotenuse. Good, so I can go to either one of these 45-degree angles. Doesn't matter. So go to this one on the bottom, arbitrarily, doesn't matter. I will go opposite, which is s, and then I divide by the hypotenuse, which is s root 2. Good. And now the s's will cancel out with each other. You will get 1 over the square root of 2. Now, I will tell you that you will usually not see it in this form. You will usually see it rationalized. Okay, so do you remember when we rationalized the denominators of functions earlier in the year? So usually you will see this as you multiply the top and bottom by the square root of 2. Don't ask me why. This is just how it usually is done. So usually you will see it as the square root of 2 over 2. All right, so for some reason, we don't like to keep square roots in the bottom of fractions. I don't know why. I don't see any issue with it, but you will usually see square root of 2 over 2. Okay, good. Now, let's just very quickly do cosine of 45 degrees, and we will be done. Okay, so cosine, we need to do adjacent over hypotenuse. So go to either one of these 45-degree angles. Again, I'll pick this bottom one. Adjacent is s, and hypotenuse is s root 2. So this will be another fraction, s over s root 2. It's actually the same thing. It's the same thing as sine of 45. Good, so this will be 1 over root 2, and then rationalize the denominator of this one. You will get square root of 2 over 2 again.